Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gill Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gill@eapen.info. My guest today is Professor Kimberly Gray, who is Professor of Civil and Environmental Engineering at Northwestern University. One of her research areas is physicochemical processes in natural and engineered environmental systems, with a particular focus on energy and urban sustainability applications. Welcome, Kimberly.
Good afternoon. Thank you for inviting me.
Yeah, thanks for doing this. So this is certainly homecoming for me, Kimberly. I went to graduate school in engineering a long time ago. But as I mentioned, lost most of my engineering. So I have to start from square one here. I want to start with your book chapter in an upcoming book on geoengineering and governance. It's about climate action, the feasibility of climate intervention on a global scale. And you say in this chapter, rarely a week goes by without surpassing yet another threshold, making our rapidly changing climate. Each season, atmospheric CO2 levels set new records. In response to the steady climb in CO2 concentrations, average surface temperatures continue to climb. You say, in fact, 17 of the warmest 18 years on record have occurred in this century. The 5 warmest years on record have all occurred since 2010, and 2017 was the 41st consecutive year temperatures higher than the 20th century average. So those statistics are all very clear. So I want to ask you sort of a broader question. Do the policymakers and the public more broadly understand where we are today?
So there are a couple of things I'd love to respond to here. So the short and direct answer to that question is no. The first thing I wanted to say, though, is, Gil, you can't ever forget your engineering. So we like to think that sort of forms this fundamental knowledge base that informs everything you do going on. You may not be able to size beams anymore for different loads, but you certainly know how to approach open-ended problems. So with that aside, the one thing I also want to comment on is the fact that those statistics you've read are, by the very virtue of how long it takes for a book chapter to make it actually into the final book, are a little bit outdated. And so if we just look at the last year, 2020, in terms of its global average temperature, is sort of relative to pre-industrial times, is tied for first place. So we have just experienced the warmest year on record, and it's second only to, I think, 2016. And in 2016, what we had was an El Nino year. So the temperatures were somewhat amplified by kind of natural events, all right? And so 2020 was not an El Nino year. So that says that, I mean, I just want to come back to this point of every year we're breaking records.
Yeah.
Every month we're breaking records, depending on, what the record is. It could be CO2 levels in the atmosphere. It could be global average temperatures. It could be, a variety of different things. And it does not seem to make a mark. It does, there has been a tremendous change since January 20th, 2021. I do think that there is the current administration realizes that we are facing a climate emergency. But what are we observing? We're observing pushback. I mean, I could give you all sorts of examples of where there's still a deep reluctance to do what it is we have to do in order to address the climate emergency in a meaningful way.
Yeah, so I want to ask you, unlike the stock market, where we cannot predict prices, in a physical system, we can predict what's going to happen because we can look at trends, we can look at how the system behaves, and we can have reasonable predictions for the future. I say reasonable because it's still a complex system, isn't it? And there is a specific definition for a complex system, right? And so how do you define this complex system of climate weather that we deal with?
So that's a great point. Our ability to predict. I think that what characterizes our current ability to predict climate phenomenon, how the climate system will respond to the radiative forcing, how the climate system will respond to CO2 levels is not great. I mean, what we tend to do is we tend to underestimate. So it's a very real experiment we're conducting here with sort of taking in all the parameters that we think are essential and then trying to make predictions about the way the system will respond. That could be average temperatures, that could be the rate at which glaciers are melting and sea level is rising, that could be CO2 levels in the atmosphere and how they seasonally vary. In general, we are underestimating. And then we make an observation and we go, why did we get our prediction wrong? And then we go back to the models or we try to fix them and we improve, we improve this ability, but there's so much uncertainty still. There's not uncertainty in the sense that greenhouse gases are warming are causing a warming effect on our atmosphere. There's no uncertainty. There is no uncertainty that we are perturbing the climate system in a way that's dangerous for human adaptation, for the sort of life support system that sustains human populations. There's no uncertainty that we're perturbing that in a way that's very, very worrisome. But to say exactly what will happen when, there's still a lot of uncertainty. But I don't think that's the problem. I mean, I don't think that's for probably, we've been talking about this since, I don't know, 1990s.
Yeah.
So in maybe the first 2 decades of this conversation, you could say that there was too much uncertainty such that how could we act? Because there's so much to lose in changing, right? So you don't want to change too soon, right? You don't, if you can put it off to the future, you know, that's better. But I don't think that's the case anymore. I mean, the uncertainty.
Yeah.
Does that make sense?
Yeah, it does. So that's one of the complications from a policy perspective. You know, without a deep understanding of the nonlinear mechanics that go on in the climate, there are oceans. We have a large biomass. We have variety of ways carbon is taken out and put back in. And it snows in Texas one winter, and politicians say, well, look, there is no global warming.
But there is. That's precisely a phenomenon of the climate emergency. That's precisely an outcome of changing climates, because what that is due to, but see, this is where, you know, your very first question to me was, do policymakers and the general population understand what's going on?
Yeah.
No, because a snowstorm in Texas is one of the symptoms. The reason for that is a weakening jet stream.
Yeah.
And a weakening jet stream means that your polar vortex gets very floppy. And when it gets real floppy, it will tend to not remain centered over the Arctic, over the North Pole. It starts to dip down. And
Yeah.
that's what happened. It dipped down, and it dipped down really far, right?
Yeah.
And what that showed is that Texas was nowhere prepared. And so now, from another policy point of view, this has happened before. It's not that this is an unimagined phenomenon. It happened before. It happened before about 10 years ago. They were warned, you need to fortify your grid, okay, to be ready for this. And they didn't.
Yeah.
Because it was an infrequent event. It's an infrequent but disastrous event. And we are very, very bad as decision makers and as policy makers in being responsive to that. And so what's happening with climate change is we have extreme events that are now happening with greater frequency.
Yeah.
So maybe that's why I'm saying I think that maybe now we'll begin to respond, because we're beginning to feel emergencies and crises more frequently, because unfortunately it's going to take crises for us to respond. We react far better than we act.
Yeah, so one of the things that you mentioned, Kimberly, is that it is difficult to predict the weather, but it is.
Wait. Say you. It's difficult to predict the weather. Is that what you said?
Yeah, the weather.
Okay.
It's increasingly easier. Well, maybe I shouldn't use the word easier, but increasingly, we are increasingly better at predicting the climate. And I want you to talk a little bit about the sort of the complex system that we are dealing with. So we have non-linear effects, and we have modeling techniques that can take into account some of these non-linear effects, but they're not going to be very good in the very short-term predictions. But that is okay, because we can make reasonably good, I would imagine, long-term predictions from a climate perspective.
So, okay. So I think that you noted that weather and climate are two completely different things, right? So, okay. So, and that the climate system is a complex system. And a complex system is a system of, just to put it simply, is a system that is made up of many interrelated parts, and that to understand the response of the system, you can't just look at the parts, right? You can't just look at the pieces of the system. You got to figure out a way to look at it as a whole. And that's what's difficult, because you don't know how all the pieces sort of come together. And so you get lots of so one of the an example of the fact that the climate system is a complex system is that I'm sure you've heard this before, that a butterfly can flap its wings in the Amazon, and that causes perturbations and in the in the atmosphere, such that it could cause a storm event in the northern hemisphere. Okay, so these small perturbations can become amplified to cause big phenomena. And it's very difficult to predict, all right? So I think it's difficult. So I think you're right in the fact that because weather is such a random process, it's so difficult for us to make predictions even a couple of days out. So there's maybe a little bit more inertia in the climate, so that you can make rough predictions over longer time periods, over longer larger scales. In general, that's probably true, but see, the system's so out of whack right now. That we're talking about there's such an imbalance in the system at the present time, and there are these feedbacks that come into play. All right. And one of those feedbacks is in the Arctic. And so phenomena in the Arctic have these both local but long range impacts.
Yeah.
And they're happening so fast that they, it's like the butterfly, the butterfly's wing flapping. So it becomes really difficult for us to make these predictions. Does that make sense?
Yeah, it does. Yes.
Yeah.
So precise predictions are difficult, but the general information. If you look at it, you talked about the Arctic, and if you could talk a little bit about what is happening in the Arctic, and again, I don't know if the general public is aware of it. We see some polar bears on this, disentangled. I don't know what the right term is on snowboards and stuff. But the problem in the Arctic that we can measure on the surface of the Earth, we can measure from space, we can see exactly what's going on. I shouldn't say use the word exactly, but it's not about precision, it's about trends, isn't it?
That's very good. So the Arctic is sort of the canary in the mine shaft, right? So what we're seeing happening in the Arctic, well, maybe I'll make a couple of points relative to what you've just said. Too often we think of the poster image of climate change is that, that sad looking polar bear stranded on a iceberg somewhere. And it's one of those things that it's so remote. Where have any of us, when have we encountered a polar bear, right? So it's sort of that, it's the furry mammal that makes you feel kind of sad, but has absolutely no meaning in our life. But what I'd like to say is that, in fact, the Arctic, which of course is so far away, very few of us will ever visit, has tremendous impacts. I mean, what's going on there has tremendous impacts on lives in Connecticut, on lives in Chicago and Illinois, throughout North America, the Northern Hemisphere. And here's, so just quickly, some of the salient events. Temperature is warming in the Arctic twice as fast as it is in the rest of the on the rest of the globe. And so you would, in fact, there's some really interesting maps that you see that show that global average temperatures in parts of in various parts of the Arctic Circle are 4 and 5 degrees above sort of the global averages from the 1880s, let's say. And that's a little bit frightening. I mean, that's definitely frightening. So why is that? Why is the Arctic warming at a rate so much faster than the rest of the planet. And does that matter? Okay, so there are some commercial and economic benefits to this warming. If the Arctic warms and all the sea ice melts, what we'll have is we'll have more rapid transportation routes, between Canada and the U.S. and and parts of Europe, right?
Also, from an economic perspective.
Sure. The other one is that if this is going to open up all sorts of opportunities for oil and gas and mineral exploration. Of course, those are the very things that are probably, causing, the problem. But on the other hand, all of that melting of ice increases the albedo of the Arctic, which then means you have now, rather than these white reflective surfaces, you have dark surfaces which absorb more solar radiation. So that in a way accelerates heating. Okay, so there's that. However, that doesn't really explain everything that's going on in the Arctic. Like, that doesn't explain entirely why it's heating so fast, because what you find is that many of these heat waves that we see happening in the Arctic are happening in the winter. They're not happening necessarily in the summer. And in the winter, there is some refreezing of that sea ice. And so that's where I come back to the polar vortex weakening. And the reason why it's weakening is sort of twofold. It's like the jet stream is weakening, and the jet stream is what keeps that polar vortex tight over the Arctic. And it's also the fact that temperature gradients, which is what also is, keeps this, the jet stream in place, are weakening because there's this overall warming. The other thing that's a big worry are some other positive feedbacks are the melting of permafrost, and the fact that there are now wildfires in Siberia, and so this is releasing enormous amounts of CO2 and methane to the atmosphere. With the warming of and the melting of the permafrost, you get a lot of, you're stimulating kind of microbial degradation, microbial action on all those peat stores, and this is releasing methane to the atmosphere. Methane is a very potent short-term global warming gas. So what we're beginning to see is a response to anthropogenic warming is the release of global warming gases naturally that will overtake what was the original anthropogenic consequence. Does that make sense? So we get to the point, we can control human inputs. We can't control the response of certain ecosystems to warming. And so that's a huge concern. So I go back to, why we need to be worried about what's going on in the Arctic. Because we have currents, both ocean currents and atmospheric currents, that are influenced by Arctic phenomenon. And that influences, like, a snowstorm in Texas.
And the Greenland is sort of a prototypical case here, right? So if you measure what's happening to Greenland, we get a good proxy for what's happening to the world.
Sure. I mean, I think a proxy. I think what we're seeing, what we need to be concerned about in Greenland, is the melting of all that land ice, all those glaciers, and big concern is, are we going to reach a tipping point? Is there a point beyond which we're not going to be able to stop it? Like, it's just, regardless of what humans do, regardless of what policy is taken internationally with respect to CO2 emissions, will the melting of that system reach a point where you can't reverse it or stop it? And there's a lot of concern that oftentimes you don't know if you've reached a tipping point until you've passed it.
Yeah.
It's very difficult to predict, like, oh, that we're teetering at this point. You know it when it's, when you've passed it, and then there's nothing you can do. You can't stop it. So I think Greenland would rate the melting of Greenland ice is going to raise sea level, 10 meters. I mean, 5 meters, something like that. No, it's not going to happen by next year, but it could happen maybe by the end of the century. Maybe, okay, so I have to think about that. I have to go back and forth between feet and meters. But if we begin to see serious melting in the Antarctic, and that reaches a tipping point, then, now, these are things that will happen over hundreds of years, but there's no turning back. And so what it does is in many ways, it sort of reverses, human living patterns that we've established over the last, 1,000 years.
Yeah, the problem, Kimberly, I think it's a sort of a runaway system.
Yes, very good.
It's a non-linear interactions, and sometimes it's difficult for people to really internalize this. So when we go beyond certain points, it at some point it becomes impossible to turn it back. And I sometimes talk to people and say, people say, why haven't we found any extraterrestrials? And I ask, would any extraterrestrials want to look at us? I mean, we have a very unstable greenhouse, and we are burning the heck out of stuff that is going to blow it apart. And so suppose we go out and if we find some kind of an ant colony somewhere, and you look at it and you say, those ants are really, really stupid. You can't really interact with them. There's a reason we haven't found any extraterrestrials, but more seriously, there is a point at which we can't really turn back, right?
Well, that's the concern. So what you read now, the latest, and when I say the latest, it's like, in the last couple of months, is that we have, 5 years to really try and get this under control. And when we say define under control, what does under control mean? We need to stop releasing greenhouse gases, and we need to start so we need to ramp down on our release of CO2 and other greenhouse gases, and we also need to figure out ways to restore the Earth system to take up CO2, because what we've done is we have altered the mechanisms by which we take up and store CO2, as we've been just liberating massive amounts through the combustion of fossil fuels. So we have about 5 years, or what will happen is we aren't going to keep this warming under control. And this is another thing I think is very difficult for the average person to understand.
Yeah.
We keep talking about 1.5 to 2 degrees C as these threshold levels. Well, 1.5 to 2, we're talking the temperature changes 1 or 2 degrees centigrade every day, right? I mean, sometimes within an hour, particularly in Chicago, right? The temperature that we experience changes dramatically over a single day.
Right.
People don't understand what this warming means. They don't understand. I think this notion of a global average temperature is almost meaningless. I mean, what does a global average annual temperature mean? When here our temperatures change by 50 degrees C. Well, no, I'm exaggerating. Would that be right? Yeah, it could, because in the summer it's way below. Yeah. So you have massive changes over an annual cycle, and we're talking about a small shift. But it's that small shift that has enormous cascading, nonlinear, and potentially tipping, or like you say, a runaway system, and the system can't correct itself
Yeah.
because
Yeah.
it's such an intricate web of connections.
Yeah, it's a systemic effect. I was debating with somebody the other day that, there's a lot of interest in terraforming Mars. And I was saying it's a lot easier to terraform the Earth.
Oh, that's so good.
You know, it's a lot easier. So let's talk a little bit about the potential solutions. So geoengineering more generally. So what are the things that we could think about to counteract the problem that we are facing?
Okay, so solutions. So one of the things I just gave this talk on Wednesday.
Yeah.
Climate change is locked in. It will happen. And it is happening, and we're not going to turn it back. Okay. So what we need to do is to see if we can mitigate the change to a level to which we can adapt, to a level that won't be, cataclysmic. So here's this, it's kind of simple. Decarbonize the economy. I mean, it's very simple. And this is something we've known for a very long time. And the oil companies or the fossil fuel companies have known for a very long time. And we just haven't done it. And the reason why we haven't done it is because fossil fuels are wonderful, right? They are a cornerstone of modern life. They've made so many things possible, but at the same time, they're going to make so many things impossible.
Mm-hmm.
So, you might want to think about them as, they were the bridge between a subsistence existence where most people lived in poverty to this, a way of life of prosperity for most people. They're the bridge. But that isn't how we view them. So the first thing we have to do is decarbonize our economy. And that will be hard, but it's not impossible. But it will take some time. And therein lies the rub, right? It will take some time. You're not going to decarbonize our economy in 5 years. You're going to decarbonize our economy hopefully by 2050. There are these various roadmaps by which we can do this, and most of them say that by 2050 we need to have maintain a net zero carbon, urban metabolism or human metabolism, or social, I guess social metabolism, economic metabolism. I'm trying to think what kind of metabolism, but we need to operate our economy and our lives such that by 2050 we're at net zero carbon. But that isn't going to be enough because CO2 has such a long lifetime in the atmosphere. It's there for probably 1,000 years or more. So we're going to have to. So all the while we're decreasing our fossil fuel use, we're decreasing our emissions of CO2. We're still emitting CO2, and it still accumulates in the atmosphere. So we're going to have to figure out ways to then remove it from the atmosphere. That is difficult.
So mechanistically, Kimberly, so we know we have a problem. We can slow down the production of CO2, but it looks like we are beyond certain thresholds where just slowing down the production is not necessarily going to solve the problem.
Right.
So we have to take out what we produce from the past.
Right.
And so if you put these two sort of the actions in the context, sort of an economic context, there could be policies we could enact to slow things down. We could have carbon trading. We could have, a lot of other things that could slow it down. But at least it sounds to me, or it feels to me, that slowing down is not going to save us anymore.
Well, if you slow down to zero, and you do it in the next 30 years, it will go a long way to save us. I don't think it will. Well, okay, so what does save mean? I mean, I think so. It will go a long way to lessening the pain, but
Yeah.
it won't eliminate the pain. So, but you know, so there was a piece, I'm trying to think, where was it NASA or was it NOAA? That I think it was NOAA, and it's looking at warming, that what the actions currently underway are not going to deliver us from, is not going to provide the relief that we absolutely need. We are so far away from what it is we need to be doing. And when I say we, I mean all industrialized countries. So an important thing to
They-
understand is that the CO2 in the atmosphere that's presently there was put there by the United States. And it was put there by the United States from like 1850 through, 1990. And I don't think people understand that. But, it's certainly the greatest emitter of CO2 now, today, is China.
Yeah.
But China did not cause this problem. It's post-industrial countries like the United States that caused the problem.
Yeah, so let's talk about this just very quickly. So we know where we are. Obviously, we didn't have all the data 100 years ago, 200 years ago. We can put fault on anybody and everybody in some sense. But at time equal to zero in 2021, as we look forward, China today emits, I think, enough CO2 as all the other countries, all the other 200 countries combined. So from a policy perspective,
are you sure that's true? Because I think that the U.S. is second. I'm not sure that's true, but they certainly are. They certainly are the major emitter now and have been since about 2006. That's true.
So let me backtrack. I don't know if that is true. I think I read it somewhere and it's not really verified. But from a policy perspective, the question would be, in my mind, Kimberly, it's more about technology transfer. So if we say that developed countries were at fault before, they have some obligation to take care of this problem. We have to apply the technology worldwide, right?
Exactly. Yeah.
Not wait for India to invent a technology to put take the CO2 out of the atmosphere. So just like the pandemic, where we have completely failed to understand the worldwide problem, here also we seem to fail to understand, the atmosphere is universal. You cannot have herd immunity in New Jersey. And just like this, you cannot have pure oxygen in California, right? So it's I don't know where United Nations is on this. Do we have sort of a worldwide psyche that is trying to solve this problem?
Oh, sure. I mean, yeah, there's the Paris Accord, the Paris Agreement, which was 2015, that was supposed to which 197 countries, I think, signed. The U.S. Under Trump decided not to be party to that, but then Biden has put us back into that. Yeah. Therein lies a very significant problem in that our approach in the United States is a wild pendulum swinging from one extreme to the other, and this is not the kind of solution. The solution to this problem cannot be something we turn on and off, turn on and off. Yeah. But that's another thing. There is no single solution. There is no technology we're going to suddenly find that's going to solve all our worries. I mean, this isn't simply an energy problem where all we have to stop doing is burning fossil fuels and going to renewables and we're going to solve everything. First of all, that would be, if we were to do just that, that would be great, right? But it's not only just that. I mean, the way in which we operate our daily lives needs to change. The way in which we integrate natural processes into, so urban infrastructure needs to change. So, and I think that's the challenge. The challenge here is that almost everything needs to change, and you almost wonder, well, where do you start? And so one start, and this was during the Obama administration, was to say, okay, the Clean Power Plan, what you're going to do is you're going to figure out how to reduce CO2 emissions from the power sector.
Yeah.
That was simply to meet those targets. And the market took us here. This is really mostly the market adjusting, was to quit using coal. So that's a great first step. We eliminate coal, but there's a consequence to eliminating coal. There has to be a change in the workforce if you're going to do that, right? You can't throw thousands of people out of work. So the economy is a complex system. We may find a solution, or one solution, because there's no single solution. We may find a component of the solution, but to invoke it is to then also require that we address other aspects.
Yeah.
And so it's that kind of orchestration of response that's so difficult. And change is so difficult for humans to address in a kind of organized, systematic way. But we're getting to the point where it's absolutely required.
Could we talk about some of the engineering, albeit somewhat tactical solutions to carbon dioxide removal, CDR strategies?
Oh, sure. And then also we should talk about geoengineering, because that one is a really, it is pretty important. So for CDR, go ahead.
Yeah. So what do you mean by geoengineering?
Well, okay. So geoengineering is how are we going to limit the warming of the atmosphere? So you can, and this is not mitigation, is to say, how are we going to reduce our emissions? But we get to the point where, all right, so let's reduce our emissions. We still are going to have problems, right? Because we've built up so much CO2 in the atmosphere. So how now are we going to limit warming? So we need to remove CO2 from the atmosphere. That's really hard to do because CO2 is 0.04% of the atmosphere. It's it's very, very dilute, but yet it really, it wields a powerful punch, right? You don't need very much to have an effect. So how are we going to remove CO2 from the atmosphere? And that's where technologies are being developed, like direct air capture would be one. You're putting CO2 through some sort of engineered device by which we're transferring it from air into a solution. You then need to remove it from the solution, and then you do something with it. And what you do with that CO2 that you remove from the atmosphere is you need to bury it. I mean, you need to sequester it somewhere where it won't, where it won't do any more damage. There's enhanced weathering, which is taking the kind of natural geochemical processes and absorbing CO2 into rock. So that's another way you can sequester it. Nature's way of taking up CO2 is through plants, is through photosynthesis.
Right.
So can we reforest and afforest the surface of the planet so that we can remove a lot of CO2? There's something called BECCS, bioenergy, carbon capture and storage, which is, growing trees, taking up all that CO2, harvesting the trees, burning them for energy, but capturing the carbon and burying it. So that's sort of a way of removing the CO2 from the atmosphere, but also seeking to satisfy the, the very real energy needs that modern life requires. So those are the major ways in which we can remove CO2 from the atmosphere. They are not necessarily fast. I mean, they take time. And for things like direct DAC, direct air capture, where you're going to engineer a process, we need a market. I mean, somebody needs to pay someone to do that, right? So there needs to be a market for the capture, because why are you going to capture carbon and then go bury it? I mean,
Yeah, I don't know the technologies, Kimberly, but my instinctual reaction to carbon removal would be that you still have to spend some energy to do it. So can we actually demonstrate it is beneficial?
well, but if your energy is renewable, I mean, of
Yeah.
course there's energy required,
Yeah.
but what you have to do is you have to tie it to a renewable energy source.
Yeah.
You can't burn CO2. I mean, you can't burn fossil fuels to run these. Okay, so you have to use you have to use some sort of renewable energy. But there's a lot of renewable energy, right? There's solar, there's wind, there's geothermal, there's tidal. I mean, there really is a fair amount of renewable energy out there that in the age of cheap fossil fuels, we didn't tap.
Yeah.
Because it was so easy not to. So, we could certainly, there's nuclear, right? I mean, I don't know, do we only use sun and wind? Is there maybe we need to look at nuclear energy? That's carbon, that's pretty low carbon.
Yeah. So you talk about biochar in so what exactly is that?
So okay, that's all right. So that would be sort of another. So biochar basically is just charcoal, right? And so it is just locking up carbon in this sort of very refractory solid material, and you can add it. You can add it to soils. Soils, returning the carbon to soils and locking that carbon up in humic materials. It will enhance the fertility of soils. When I say fertility, it basically changes the structure of soils so that they can support plant growth better.
Yeah.
Because it's adding to the organic fraction of soils.
Right. Yeah, this is so interesting, Kimberly. We'll take a quick break. When we come back, we'll talk more about this.
This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.
So we are back, Kimberly. We were talking about climate change. There are multiple things we could do. We could reduce carbon emissions. We could take CO2 that we have already produced, take it out of the air. We might be increasingly moving in that direction because slowing down gets us only so much from the point we are on. We were talking about biochar just before the break. So this is something that will allow us to take sort of a carbon sink, isn't it?
Yep. But what's so cool about biochar is that in making it, so you take organic material and, just like you would if you're making charcoal, and you pyrolyze it. So you're going to combust it under, in the absence of oxygen. And what you can do in making biochar, you can, you yield energy. So you can get like, I don't know, 5 times the amount. I think it's anywhere from 4 to 9 times the energy you put in out of it. So in this conversion process, you can gain energy, plus you have the biochar material, which is in which you've stored carbon. I just think that's so cool. We need to think. The question though is, how much can you scale that up, right? So that sort of phenomenon, where could we actually be doing it? How much energy could we gain from it? How much will it, address the CO2, the CO2 uptake, the CO2 storage issue?
Hmm.
And that's the part where, where we can we model it? So we need to remove like 10 gigatons of carbon from the atmosphere each year until 2100. So to what extent can this biochar industry or cycle address that, 10 gigatons per year? And that I'm not quite sure about.
Right. But it seems like a win-win, right? I mean, if you can
Yes.
get energy out by sequestering carbon, it seems like it's something that everybody should be doing everywhere.
Of course. That's what I mean. I mean,
Yeah.
there are, but okay. So this brings up a really interesting point. That's difficult. There was enormous industry and technology that evolved around fossil fuels. So coal or petroleum or methane. And so it's, and what we're talking about is a future in which you would have many types of energy sources. So you'd have a big menu that would be kind of locally tailored. And so that's really moving from something very large scale and almost uniform to something that now is just highly heterogeneous, highly variable. And so and very distributed. So in a way, it's a different kind of thinking. It's like sort of a network economy rather than this economies of scale. Of like the similar kinds of technologies that you operate at enormous scales that are kind of the same, going from place to place.
Yeah, so that also has some beneficial effects for developing world, I would imagine, right?
Of course.
Yeah.
Oh, absolutely.
So is this a technology that we have, or it's something that we need to develop?
Oh no, we have it. There's no new technology there.
Yes.
No, scale. I mean, you'd have to. I mean, I think there's a scale issue. There's a distribution issue, but there's no new technology.
Yeah, I mean, scale and distribution, as you know, are engineering problems. If you put Northwestern engineers on it, they will solve it. So why haven't we done this?
Okay. So I think we're coming back to the question you posed to me at the very beginning.
Yeah.
We're not doing this for, I think, I'm going to be simplistic, 2 reasons. One, because there isn't the imperative, there isn't the urgency, and there is, how are you going to start the market? So there either needs to be policy or incentive. How will you incentivize this? Or there need to be regulations. Well, we have just emerged from one of the most anti-regulatory periods probably in our history. So government and regulations are really dirty words at the present time. I don't understand it. I think this has been the reason why we've had such a dismal response to the COVID pandemic. And I think it's why we just failed to act on climate change. This emergency that will maybe unravel life as we know it.
Yeah. So I want to talk a bit about photosynthesis quickly. Nature has very efficient solutions to it, except we don't take that up. Are we beyond the window where we could apply some sort of nature-based solutions, or is it too late?
Oh, no. I don't think, well, okay. So I don't think that we can employ only nature-based solutions.
Yeah.
I think that nature-based solutions for, many of our requirements, human life requirements, are just there for the taking, right? So ecological goods and services are invaluable, and to our economy, I just think that they're not well acknowledged as such, right? So our food system is a critical ecological goods and service. I think there are lots of infrastructure systems that we could rely on, excuse me, nature-based solutions. For instance, stormwater management, flooding control. I mean, all of those things are things that we could do. We do primarily with pumps and pipes, but it doesn't serve us well. It doesn't serve our interests short-term or long-term well. We could rely more on green infrastructure systems, on ecological goods and services, and have cascading benefits. We tend as engineers, I think, sometimes to engineer very narrowly. We have a goal, and we design for that one goal. We don't, whereas nature is a more intricate fabric. And so, photosynthesis is kind of an inefficient process. It's what, 1% efficient, but look what it does.
Yeah.
Look at what it provides us with that low efficiency. So, but it's that low efficiency, but in a very diverse system. And I think what engineers have wanted to do is to have uniformity and high efficiency.
Yeah.
I mean, yeah. And I think that undermines resilience and adaptability.
Yeah. No, so much interesting stuff in this, Kimberly. I can get to all of them. You talk about engineered solutions to engineered problems. You talk about unintended consequences of the engineering mentality, which I can relate to. I have seen a lot of interesting sort of ideas, especially from an economic perspective. With the great politicians that we have around the world, it's quite possible that we would have missed the window of taking care of it gradually. And if so, what do? We come to a point of, survival. Do we have some sort of, solutions where we could say, yeah, we completely screwed it up, let's do something different?
I I think I know what you're getting at. So it's, what's our life vest? What are we going to do if the ship goes down? So there's a lot of thinking now about things referred to as geoengineering. So let's say that we continue along this business as usual path, or we continue along this sort of failed policy path, which is where we are. Like we're making a little bit of effort here and there. It's, it doesn't accrue to this continued wave of mitigation. And so we just find ourselves in the point where, oh my God, it's getting too warm. We've warmed the planet too much, and it's out, and there are too many people living in this, belt of really intense heat, and they can't survive. What can we do? How could we immediately cool the planet? Well, there's some thoughts about ways in which we could provide a sunscreen. Is there some way we could put a sunscreen around the globe, around the planet, so that we could just cut down on the amount of light coming in and the amount of warming? So and this is called solar radiation management. It's a geoengineering technique by which you could put something in the stratosphere that would reflect the light, the incoming solar radiation, so it doesn't hit the Earth's surface. And that'll cool it. We'll just cut down on the amount of light coming in. And so in fact, this happens naturally. If you have a volcano that spews up a bunch of sulfate particles, or SO2, and that forms sulfate particles or aerosols in the atmosphere, you can get a temporary cooling of the Earth's surface. I mean, we've seen it in the past when there have been big volcanic eruptions. So maybe what we could do is copy nature. We'll just put a bunch of sulfate aerosols. We'll fly, supersonic jets around the stratosphere, and we'll spew out these aerosols. In fact, this is called stratospheric, aerosol dispersal, or something like that.
This is sulfur dioxide?
Yeah. Well, it turns into sulfate particles, SO4, but you get the oxidation of the SO2 in the atmosphere. So yeah, you spew out SO2, it forms these sulfate aerosols, and that will reflect back. The little aerosol, the little water droplets will reflect the light back, and that'll cool. And there are a lot of people who say that this is a solution that is safe and easy and rapid. Now, here's the thing: you've got these sulfate particles, these aerosols will eventually fall to Earth, right?
Yeah.
So you have to maintain them, and there are some potentially unintended consequences. One of the consequences is that this is a moral hazard, meaning that if we go up there and we figured out this way to cool the Earth's surface, then what that does is it takes away the pressure to reduce to address the fundamental problem, the root cause. The root cause being our profligate release of CO2. So that's the moral hazard question. The other thing is that you've got to maintain this sunscreen, this aerosol sunscreen. If you ever stop, you're going to immediately get a huge jump in temperature, right? Yeah. And then the third, there's a whole big list of them, but you need to do this everywhere. So there's the potential to weaponize this technology. So you could put too much or too little. And I don't know that we understand the Earth system well enough to know. I guess you would experiment as you figure out, the rate at which you need to disperse these aerosols and where. But it's very likely that you're going to alter the hydrologic cycle too. So there's a connection between the kind of Earth's energy, the energy, the solar radiation cycle, and the hydrologic cycle. And these are long-term cycles. And so the thought is that if you start to cool certain areas, like you can't just go and cool the globe uniformly, right? So if you cool certain areas too much, you're going to reduce the amount of evapotranspiration of water, and then that may you may also change air currents and the transport of that water, because evaporation of water in one part of the Earth causes, like in the Amazon, can influence sun rainfall in another very distant area. So it's on. So for instance, could this alter the monsoon in Southeast Asia? So there's a concern that possibly by cooling parts of North America, we could have unintended and unpredictable changes in hydrologic cycle, let's say in Southeast Asia. And it would take, it's hard for us to understand all the couplings to make that prediction.
Yeah.
So we absolutely know we could reduce the Earth's temperature, the heating of the Earth by this technology. But we don't know all of the social and physical consequences of it.
Yeah. The unintended consequences really worry me about this, Kimberly, because they're not really predictable. So in conclusion, we sort of have three cohorts of humans. We have politicians, we have the general public, and we have scientists and engineers. And they seem to be living in different worlds for a variety of reasons. So as you look forward, look forward 5 years, you mentioned that we have a 5 year sort of a window where we have to make a significant impact on this problem. Um, what do you see? So where do you see things are going to improve? Where do you think we should focus on? If you think about these three buckets of people, it's really a difficult problem because of the nonlinear aspects of this that we talked about. It snows in Texas, and suddenly global warming is off the table. And then you have scientific and engineering data, but politicians don't really care about it. So where do you think we will be 5 years from now?
Well, I hope that over the next 5 years, we see real action and deep action. And I think that will come about because of the power of leadership. We have to hope that we witness leadership that can inspire and that there's a willingness to follow. I mean, it's not just, it's not, I mean, a leader's only as good as the people who decide to follow. So what I worry about is that we're really in an era of distrust and an era of cynicism. And that I definitely worry about that. But at a certain point, if we have another year, like we had last year with hurricanes, I mean, if this keeps happening such that, it makes a mark, an indelible mark on people's memories, I think, and if enough people feel some pain, then I think it will happen.
Yeah. Excellent. Yeah, this has been great, Kimberly. Thanks so much for spending time.
Oh, you're so welcome.
Thank you.
Thank you.
Bye.
This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.